Hi, I'm Dengyu. Today I'm gonna talk about our effort and preliminary results on topic nanoscale programming of ferroelectric thin films using ultra-low voltage electron beam lithography. Mm, Quantum simulators permits the study of a quantum system in a programmable fashion, and we have several well-developed platforms for analog quantum simulation right now, such as the ion traps and ultra-cold atoms. Uh, they show different length scale and provide a great platform on understanding the quantum simulation and Hubbard model simulator. But the question is, are there any other platforms that we could study, especially in the solid state platform, to synthesize this analog quantum simulation? And we believe controlling quantum matter lies at the center of this question. The quantum matter we're interested at is especially the two-dimensional materials, the van der Waals materials such as the graphene or bilayer graphene. It has been shown that the twisted bilayer graphene shows band engineering with the emerging secondary lattice structure, Moiré superlattices. Also, it shows novel solid-state phases, such as reconnecting and mott-like insulator states that has been never been observed in the graphene systems. So people have proposed using these twistronic systems as a robust quantum simulation platform for its strong correlation of the system to be studied or and the topology of the system. It has advantages as different aspects, such as the tunability, which the external parameters that can be tuned, such as gating, applying a strain, or different stacking together, or the twisting angles. The feasibility, such as these, we can realize and control the large number of fundamental many-body sites. Also, the availability, which means the readout protocols can directly be mapping in and out of the equilibrium states in the phase diagram. So it's a very good system for quantum simulation. Not only the twisting, but the electrostatic gating can also achieve the band engineering of the graphene system, such as here they use etched silicon dioxide as a dielectric layer and gate the graphene into this lattice structure shows the extra direct peak. So our goal is also creating a two-dimensional quantum simulation platform, but using this powerful tool called ultra-low voltage electron beam lithography, reaching the van der Waals materials, band engineering, novel phases emerging, and so on, and furthermore reaching the quantum simulation, such as using this ULV-EBL tool, we can input different model that can come from a calculation of the theorists and make any artificial layouts we would like to pattern for the 2D system. And we can choose the materials we would like to study, such as a combination of complex oxide structure with 2D materials, and we would like to see outcomes from this ULV using the ULV-EBL patterning, such as see if we can simulate the 2D Hubble model or study the quantum spin liquid states. To do that, I would like to introduce our new technique that we established called the ultra-low voltage electron beam lithography. It can we first demonstrated it at the lanthanum strontium titanate heterostructure, which is a complex oxide heterostructure with two-dimensional electron gas formed at the interface. The ULV-EBL can reconfigurable pattern nanostructure at the LLS2 interface, patterning the conducting 2D electron gas system. And furthermore, I will show you it can write through a 2D layer on top and reach the dynamic gating. To show the writability of the ULV-EBL, we have the 3.4 unit cell LAO on the steel substrate, which is insulating but highly tunable, with two interface electrodes connecting to the interface, with exposing a nanowire directly by the e-beam. We can see the conductance jump from the in-situ monitoring of the conductance. That means we can use this to pattern conducting nanostructures at the interface. And the writing process is reversible. It can be cut totally to zero conductance by a negatively biased AFM tip. Furthermore, we transfer the graphene and boron nitride van der Waals stack onto the LLSTO, and with patterned nanowire connecting the electrodes across the stack, we can still see the conductance jump, which means the ULV-EBL can write through top layers and pattern the 2D electron gas underneath. So our goal is to use this method, take advantages of this method to create these reprogrammable quantum materials, such as we have the van der Waals stack on top of the substrate, and use the programmed pattern to dynamically gate the graphene or bilayer graphene into such as lattice structure. As I said, we demonstrated this first at the LSTO, but in this talk I will show you not only the complex oxide structure, but the ferroelectric thin film can also do this. So it has been shown many years ago, back to 1992, that direct E-beam irradiation can switch the ferroelectric polarization, thus pattern the ferroelectric domain on the ferroelectric material. But at that time, the study is not the patterning parameter has not been optimized, such as the characterized writing resolution, the penetration depth of the writing, and the dose are not optimized. And furthermore, they did not show if they can integrate with other materials, and that's important as a functional material. So we work with the aluminum nitride ferroelectric material with boron to substitute part of the aluminum, and this kind of material shows very high order charge carrier polarization with as high as 10 to the 14th to 15th order per centimeter square surface charging. And that's fascinating. It's really hard for other materials to reach this carrier level. Also, Dr. John Paul Maria's group from PSU provided this film, and they can grow it in a very thin fashion. The film can be as thin as 5 nanometers, with thickness usually from 5 to 20 nanometers, which allow us to integrate with other materials. This is the initial demonstration of the patterning of the ferroelectric domain using the ULV-EBL. Here I used the E-beam directly expose this ferroelectric thin film into this P letter standing for PET and PSU, and after that I use an AFM tip to scan it. I can see clearly under AFM AC scan the different surface charging gives me contrast on the signal, and here is a PFM scan showing the different polarization from the different piezoelectric response from the different polarization. Also, we study the resolution of the writing. Indeed, higher dose will give worse resolution, but here with a certain dose, we can see the wire is as thin as 40 nanometers or less. So that means the writing resolution can be smaller than 40 nanometers, which is in order of the granular size of the ferroelectric domain cell. This is another AFM characterization to show we are able to see the pretty sharp tip from this triangular shape exposure. So a good way to test if we switch the polarization totally is by etching. Basically, aluminum nitride will interact actively with KOH, but the different surface energy will give a different etching speed, and they can differ as large as 10,000 times. That means one polarization will be etched away, but the other will leave there. So with 2,000 2 kilovolt acceleration voltage of the E-beam, I can see from the Monte Carlo simulation the electron beam can penetrate through all the aluminum boronitride layer of 20 nanometers, and after 1 minute etching, I can see this 20 nanometer step clearly. That means I flipped the polarization of the film totally. So our goal is to do gating to the van der Waals structure on top using this patterned ferroelectric film with high order surface charging differences, and we're looking forward to deliver you future results from it. And thank you.